This presentation provides an overview of Chapter 9, Part B, in the book titled Simple G, a gridded economic approach to analysis of sustainability of the Earth's land and water resources, edited by Aman Hakiki and Thomas Hurdle, and published by Springer. This slide provides an overview of all chapters in the Simple G book, each of which has an accompanying presentation to motivate the material covered in that chapter. During this presentation, I'll cover a portion of Chapter 9, which is on model validation, comparing gridded and regional simulations to observations. Previous chapters laid the groundwork by providing theoretical foundations, introducing general conditions, specifying mathematical equations, discussing the gridded data and parameters, and computer implementations. In this chapter, we'll focus on verification and validation of the model. Geospatial economic models such as Simple G have to take into account multiple drivers simultaneously, such as population growth, technological advancements, and policy changes. In other words, land use is interconnected with socioeconomic, environmental, and climatic variables. The complex interactions between these factors require careful consideration during validation. Data limitations, measurement errors, and incomplete information make it difficult to validate the models against observations. Predicting and validating models under such dynamic conditions is quite complex. To ensure the robustness of the geospatial economic model, a multi-pronged validation approach is crucial. This includes sensitivity analysis, where you vary the key assumptions and drivers to understand how predictions change, pinpointing critical model components. Uncertainty quantification helps identify potential sources of uncertainty and their impact on conclusions. Additionally, benchmark replication compares model outputs to real-world data for the base reference condition, ensuring the model replicates reality. Finally, backcasting involves using the model to predict past events and comparing them to historical data. This step validates the model's ability to capture underlying economic and spatial processes. We've assessed the performance of the Simple G model in predicting the spatial distribution of cropland from around 2001 to 2016. Our evaluation is based on the most significant socioeconomic drivers of land use, including global changes in population and income, biofuel mandates, changes in productivity, and shifters in land supply, which are exogenous to the model. We then compared the simulated cropland generated by Simple G with the observed cropland using the National Land Cover database. This figure shows the projected cropland area from Simple G that is aggregated over all the grid cells from 10 km nominal resolution and compares this to the cropland area reported in the NLCD, which is aggregated from 30-meter resolutions to the same grid cells. A visual comparison shows that overall, the projections are close to the National Land Cover database. This figure decomposes the drivers of change in cropland as projected by Simple G and shows that for some regions, such as the fruitful rim that includes California, the supply and demand drivers are working in the opposite direction. Thus, depending on the magnitude of the drivers, the projections can have higher uncertainty and lower accuracy. We've also performed sensitivity analysis for this model. The figures on this slide are based on 241 runs of the Simple G model with different combinations of parameter values. The bar charts show the sensitivity of the projected irrigated area to each parameter, where ECRP is the substitution elasticity, EWAT is the water supply elasticity, ELND is land supply elasticity, and EREG is the product differentiation parameter. On the right-hand side, QCrop refers to crop production, and QLand refers to cropland area. If you're interested in learning more about validation of geospatial economic models, Please review Chapter 9 of the Simple G book, where you'll learn about global and regional validation, with a focus on Simple G US and Simple G Brazil. Here, you'll find additional readings and references you might be interested in further exploring. On this slide, you'll find the link to the Simple G webpage where you can find additional resources, as well as links to the book and other chapter presentations. Lastly, we also gratefully acknowledge support from the U.S. Department of Energy, the Department of Agriculture, and the National Science Foundation. Thank you for watching this presentation on the Simple G book, Chapter 9b. We encourage you to explore the other companion videos that accompany the book on the Simple G webpage.